Good morning, class. Today we're going to be taking a look at particle systems. So we actually have a whole starter project I've gone ahead and put together for you. This is based on a sample from the original XNA samples, but there's been a lot of changes to it, so especially for A, readability, and B, for efficiency that I've thrown in. So I figure we should spend a little bit of time and talk our way through why and what we've done there, as well as just talking about particle systems in general, and then implementing some of our own. So to start with, what is the point of a particle system? What is a particle system? Well, a particle system takes a image, a texture, like for example this particle image, and just repeats it multiple times, draws a whole bunch of them, thousands potentially, and overlaps them, lets them blend, and uses that to create complex effects like waterfalls, precipitation, fire, explosions, smoke, little fairy sparkles, all kinds of interesting things that we can do with these. And because they're actually drawing thousands of sprites on screen at a time, it's very important that we try to be as efficient and careful as possible in how those are actually drawn. So we actually take advantage of a couple different strategies as we're doing a particle system. The first is the flyweight pattern. So every particle has a few things that are unique to that particle, and then it has a lot of things that it shares with every other particle in the particle system. So we separate into a particle system and a particle those various things. So let's take a look at the particle first. So we've declared this as a struct, and by declaring it as a struct, that means it's a value type. That's going to come into play here in a bit when we talk about locality, but for now just know that it's a struct. We have a position vector, a velocity vector, an acceleration vector defining the linear dynamics of this particle. We have a rotation, an angular velocity, and an angular acceleration describing the rotational or angular dynamics of this sprite. We also have a scale so we can vary the size of the sprites. We have a lifetime, which just says how long the sprite should live before we're done with it. Usually particles really have a short lifetime. They are spawned, they move in some interesting form, and then they disappear. We also keep track of the time since this individual particle has started. It's how far into its lifetime it actually is. And then a color. Now all of these properties are, at least in our idea of how this particle system is going to work, unique within that particle. If you've got a particle system where everything is shared, like all the velocities are going to be the same, we could actually take this out and then just handle the velocity in the particle system. On the other hand, if you needed an additional value that made particles unique, you could add that in. So this is a little flexible. We really want to only capture the things that absolutely need to be captured that are unique on a per particle basis within the particle struct. We've also got some initializers here. Notice that we take a vector where we're going to position this, and then we have a lot of these default values. And the nice thing about using defaults like this is that when we invoke this initialize, if we want to set, say, just the rotation but none of these other values, we can provide the where vector, and then we can say rotation colon and the value for the rotation. We don't have to supply all these additional ones in between. So this gives us a very flexible way of kind of declaring it. The downside to this approach is this kind of default specification can only work for things that are compile time constants. That means primitives. So floats, booleans, ints, uints, doubles, those will all work just fine. However, vectors, which are a struct, or colors, which are an enumeration, can't quite be handled that way, so we actually have to actually, no, color is not an enumeration. I'm pretty sure that's a struct. That is a struct. So structs we can't do that way. So we do have to provide a couple overloads to allow us some flexibility there. So I have a overload that takes both the velocity and acceleration, an overload that takes the velocity, acceleration, and color. So 4 total defined initialize methods. Also note that we're not using the constructor here, we're using an initialize method, and that's because once we've created that particle, we're going to end up reusing it, and that's part of our second strategy for saving memory, which is what we call a resource pool. We only want to allocate as many of these as we need, and then we're going to reuse them when we're done with them. That's also why we have this active property. So once a particle is dead, we can reuse it, bring it back to life, use the exact same memory, and then we're not allocating and deallocating memory every time we need a particle. And that's a really good thing, because if we are allocating, deallocating every time we need a particle, which is going to be about every frame, maybe several hundred times a frame, we'll end up chewing through a lot of memory and throwing a lot of garbage out there for the garbage collector to come collect. And if the garbage collector kicks on during a game, that's a lot of extra processing that can lead to basically freezing your game while the garbage collector does its work, and then so you get these really glitchy pauses where your game just stops running for a moment and hangs, and that's not generally a good design idea either. Okay, so particle, just the stuff specific to a particle. Now let's look at the particle system. So the particle system is also a class, and we've got a couple constants we're defining for the draw order. Notice that we're actually extending from drawable game components. Let's start there. We've already talked about drawable game component in our architecture discussion, but basically it is a class that implements an update method, a draw method, a initialize method, a load content methods, all those things we've already dealt with, plus a couple of events. What its real strength is that there is a list of game components in our game that we can add new game components to, and the game will automatically invoke their initialize, their load content, their update, and their render at the appropriate times. So that leaves us with a very hands-off system. We just declare it, we pass it to that, or add it to that collection, and we don't have to interact with it after that point. Now, if you do want to have more control, there's nothing says that you have to put that drawable game component derived class into that components list. You can still manually call the update, the draw, the load content, the initialize yourself, just like we have with some of our Sprite examples earlier in the course. So this just gives us a lot of flexibility in how we'll use these systems. So one of the concepts there is that with the drawable game component, if you're letting the game take care of its draw, it sorts those according to a draw order property, which is also part of the drawable game component. And that makes sure that if you have things, for example, that you're using transparency, they need to be drawn after the background, kind of following that painter's algorithm, we can do that. And when we're working with particles, there are different ways we can use alpha blending. So there's the traditional alpha blend, which means if we have some transparency in our image, we let the color of the background show through and be tinted by the, if there's opacity, if there's true transparency, it just shows through. If there's opacity, so you have like an opaque red glasses that your character is wearing, rose tinted glasses, that makes everything that you're seeing through that lens look redder than it normally is. So that's traditional alpha blending. Additive blending is a little bit different. It takes the colors of what we're showing and blends them, basically adds that color to the color in the background according to the color channel. So if you have very red object in front of things in the background, we add the red color to the red channel in those background objects, plus the blue channel, and the green channel, the green channel. And the result of that is that if we have a bunch of particles clustered together, they start to really just make a bright white color because they've amped up all the color categories to their maximum, which is 255, 255, 255, or 111, depending if you're using the float or integer representation. Basically means the color channels are completely on. And that works really well for fiery kinds of effects. For example, an explosion, usually at the center of the explosion we have a very bright white area, and then as it flares out towards the edges it gets redder. Or with a fire, at the heart of the fire we usually have a bright white, and then it becomes yellow and it fades to more of a reddish orange color at the edges. So that can really give us a good looking fire effect. But we want those kinds of things to be drawn on top of the alpha blended things. So we just hard code a couple constants that we can use. We're not required to. But that's really what the concept behind there is, that if we want to actually specify drawing order values that we just use throughout our game. Then we have a Sprite batch and a content manager. And this is one of the places I varied from the sample. The original sample used the one out of the game, but the game class, the game 1 class derived from the game. The game itself does have a content manager, so we could actually use its content manager, and the Sprite batch is actually added in that game 1 template, so it may or may not be there. I just figured it was easier to push these down in the particle system and initialize our own to just always have them available, but at the same time we don't want to create a new one for every new particle system we work with, so we make these static variables. That means there is going to be one instance that's shared amongst all of the particle system classes, so everybody who inherits from particle system is going to get to use these too, and I'll show you how to initialize those correctly in a bit. Then we get down to our private fields, and this is where things get really interesting. So we have our particle array of particles. And this actually ties into two ideas. One is the object pool, the idea that we don't want to allocate more memory than we need to, and we want to allocate it once and never reallocate it. And the other idea is the data locality. So let's kind of talk through what these are doing. So we have a particle array, and then we have a queue, which is keeping track of the index of free particles in that array. So if I were to draw out kind of our memory, and if I'm using an array, we know that that means in memory we should have, I'm not terribly good at drawing straight lines apparently, we should have our memory kind of laid out like this, where each one of these boxes represents a single particle. And this is one of the things is why we decided to use a struct instead of a class. If we used a class, then every time we initialized a class, we would actually initialize it somewhere else in memory on the heap, and our array would point at that in memory. So these would point at different spots in memory where those were allocated. If we'd allocated them all at the same time, there's a good chance they'd be next to each other linearly in memory, but they're not guaranteed to be. Now, on the other hand, if we declared this, the particles as a struct, that means the actual particle data ends up sectioned off inside these individual cells. So I'd have a cell which is the first particle's data, and a cell which is the second particle's data, and a cell which is the third particle's data. So that very first one would be maybe the position, the velocity, the acceleration, the color, and kind of down the pipe. But the difference is these are all linear in memory, these are not. And that's important when we start talking about cache coherency, which is something we have in the modern CPU. So in the modern CPU, you have kind of your registers, which in a 64-bit system are 64-bit memory locations, and that's what we copy things into to do our calculations, so things like addition, subtraction, multiplication, division, etc. And the thing about registers is they are fairly small, and they really just hold a single value unless you're doing something extraordinarily fancy. That's pretty much all they're going to be, and they're all the same size. I'm not drawing them the same size. That's kind of a mess. It's not really what they should look like. Can I erase these and try again? So sorry, I should have had a pre-drawn diagram for this. But basically we have a bunch of small locations where we can hold single values. Then there is of course there is RAM, which is what this is actually representing. This memory that we're drawing right here, this is our RAM. So this is where we're storing all the program's values while the program is running. In fact, we're not just storing the program's values, we're also storing all the program code in there, all of the methods we've defined, that all actually ends up loading into RAM and being used from RAM. And if you remember from your computer architecture class, the actual space that we allocate for our program, we actually get three places. We get the static memory allocation. So the program itself, anything that's declared static, all of that gets allocated in this first run of memory. Then we have the stack, and we have the heap. And the heap or the stack is where when we declare a instance variable in a method or a class variable, those all get allocated on the stack, and that stack grows this direction in our available memory. And our heap is where all of the stuff that we construct by allocating memory. So anything we construct with a new keyword technically ends up on the heap out here, and then it grows this way. And so the stack is fairly predictable. The heap kind of gets to be a jumble, and that's where garbage collection happens, is all the stuff on the heap gets collected that way. The stack is actually, because it's based on frames and based on method calls, so as soon as a method call ends, the memory that was allocated for in the stack goes away. And this behaves very much like a traditional stack data structure, hence the name stack. Whereas the heaps, we just kind of throw stuff at it. And the garbage collector cleans it up and rearranges it every now and then, tries to make good use of that memory. So when we allocate an array, we actually allocate it all in linear memory like this or like this, but the difference is if it's an array of structs, then the entire structs value stuff is actually in the array itself. And if it's an array of classes, what we're actually storing is just a reference to another point in memory where the actual class is. So this would be just the address. And if you remember doing C#, this is pointers is what we're talking about. This would be so we would be storing a pointer to another location memory where the actual allocation for that class data was. And that's why we like this one. And the reason we really like this one is when we copy things out of RAM, so say I in my code say I want to get element 2 out of the array, so either this element or this element, we are going to copy that up into eventually the registers, or just a particular value out of these to the registers. But we're also going to copy some of the memory around it, and we're going to put that into the L2 cache. So the L2 cache is just an area of very fast memory that's very close to our CPU. So RAM itself is huge, comparatively speaking, and it's located in RAM chips on our motherboard, so it's some distance from the CPU. The L2 cache is implemented, if I remember correctly, on the motherboard itself, right next to the socket of the CPU. And then there is also an L1 cache, which is actually located on the CPU die itself, so it's right there next to the CPU. And actually I've drawn these incorrectly because the L1 cache is smaller than the L2 cache. And actually there is usually a separate L1 cache for every CPU. So if you have a multi-core CPU, every core gets its own L1 cache. The L2 cache is shared, I think, in most architectures amongst the various CPUs. And some of that is obviously changing. There's a lot of new ideas coming out there in terms of how to actually organize a CPU. But the idea of the caches is fairly standard, that what we're going to do is we're going to copy from RAM some chunk of memory, which is enough to put into this L2 cache, and part of that we're going to hack out, and that's going to go into our L1 cache, and from there we're going to pull the values that we need for our registers to do our calculation. So the benefit of this is when we go to RAM, we don't just grab the one cell that we're interested in. We actually grab that cell plus some data immediately around it. So if we grab that one and we grab this one, the difference is here we're grabbing the actual values we need to compute with. So those would be loaded into our L2 cache and our L1 cache, which means we don't have to go all the way back down to RAM to get the next one if we're iterating over this collection. On the other hand, with these pointers, if we start with this one and we copy this memory out, well, we have to go and hit RAM to get this guy, and we copy that in. This gets thrown away, and then when we're ready to hit this next one, we got to come back down and hit RAM again, and then hit RAM again to get to this reference. That's what's called a cache miss. When the next piece of data you're looking for is not in one of these caches, you have to go all the way back down to RAM. So the amount of time it takes to go to the L1 cache and back is much shorter than the amount of time it takes to go down to the L2 cache and back, which is much shorter than the amount of time it takes to go to RAM and come back. So ideally, if you can keep most of your interactions on this level, especially when you're iterating over a large collection, your program's going to run immensely faster. And that's completely based on the hardware of the system you're running on. It has nothing to do with the programming logic. So the programming logic is exactly the same in terms of accessing memory, but the actual implementation on the hardware side is where this difference comes in. And this will add up very quickly. You'll actually see a a significant performance gain when you can avoid cache misses. So that's why the particle itself we defined as a struct instead of a class, and that's also why we're using an array instead of a list or something like that. We could theoretically use a list because it does tend to use at least the C# implementation uses an array list underneath, which is an array structure. But if we declare it this way, we have no ambiguity. We know what we're getting. This is going to be all consecutive memory, and the individual values describing the particle are right there in the array so that we can really minimize those cache misses. And then we need some way of keeping track of which ones of those we have actually finished using. So say this one has died, we want to come back and reuse this at some point. So we actually have a second queue, which is just holding indices in this array of which ones are available for us to use. And that's part of that object pool idea. So rather than allocating and getting rid of a bunch of objects, which causes a lot of allocations to happen on the heap that we then have to delete and come back and garbage collect and free up this memory for use again, what we're actually doing is we allocate one big chunk in the heap, and that sticks around for the entire game, and we just keep reusing chunks of it. So we're actually taking over some of the memory management ourselves, at least in terms of these object pools. Okay, so that's what these two things are about. Then we also need the texture that all the particles in the system are going to use. This origin is just the center of that texture that we're going to calculate. We talked a little bit about the blend state already, so we're defaulting to alpha blending, which is the kind you're used to, and then we'll potentially override that. Notice it's protected, so any class we derive from the particle system, we can change what that is actually using. The same with the file name for the texture, and then this min and max num particles is used to determine how many particles we want to spawn every time we spawn particles. Then we have a free particle count, which we need for our own internal calculations, and we go ahead and make it public because it just basically becomes a read-only property, so there's no harm in showing it to the outside world, and it can also be useful in like debugging to figure out am I running out of particles. That is one of the downsides of that object pool, is that if we have all our particles are alive, then we have no free particles to actually go ahead and create more particles, which means we probably need a bigger array to begin with. And that's why, for example, we actually pass in this max particles property to our constructor. We use that to determine how big that array is actually going to be. So because we are inheriting from the drawable game component, we do need to take a game and pass that to the base constructor so that it can initialize the game property. We go ahead and create that particle array, and we also create that queue of free particles. And notice that we pre-allocate enough memory to hold the index of every single particle in our particles array. That way this never has to reallocate space. This queue is always going to be big enough and just the right size to hold all of the indices, which is actually what we're going to initially start out with, because we're going to iterate over that array. We're going to initialize all those particles so that their values start where we want them to be, and then we're also going to enqueue all of the indices of each one of those particles in this free particles queue. So it's a first in, first out. So basically the first one we're going to add is index 0, so that's the first one we're going to actually populate, and then we'll just keep populating as we go across. So that's a nice easy way of kind of keeping track of that. Now it is a bit more memory. We basically have two data structures that we're using in conjunction to kind of lay out where our particles are in memory, and then where we can add new particles within that object pool. But it actually pays for itself in terms of the savings and the calculations itself. And then we do this Initialize Constants, which is a hook function. So let's talk about our hooks. A hook is basically a method that's intended to be overridden, and it provides a way for you to add your own custom functionality into a class that exists. So in this case, the particle system. So when we want a particle system to do a specific kind of effect, we're going to create a new class derived from particle system that's going to supply that effect. So this could be, for example, maybe we're making a fire. In that case, we want our particles to move upwards and change their colors maybe a little bit and size over time, and set a specific amount of time we want them to survive. So we'd want to go ahead and set that up, and that's what some of these the hook methods are for. So this first one, Initialize Constants, is really to allow you to set the blend state, the texture file name, and this min and max particles. And notice that the base method really doesn't do anything, so it's just there as a hook. We could in fact make this abstract, and maybe we should. Yeah, let's go ahead and do that. Abstract. Of course, we make that abstract, the class itself has to be abstract. But that just reinforces the idea that this class is not meant to be initialized itself, but actually it should only be used as a base class, and that any base class that implements this has to go ahead and have this initialize constants. And then because we've made it an abstract method, it doesn't have a body. So this is you have to implement or initialize. Then we also have virtual methods for initializing individual particles, and notice that we're passing this by reference. So particle is a struct, remember, and by default when we pass structs, what we're actually passing is not the structure, not the memory of that struct where it is in memory, but we're actually making a copy of the values in that struct and making a brand new structure that we're passing. So when we put the ref keyword in front of that, that's saying no, I want to pass this by reference. So I want to actually give you the exact memory location, so the exact particle that we're working with. Not a copy of the particle, but the exact particle we're working with. And that's important because we want to actually initialize that particular particle. And then we have the p.initialize, we're calling with the where, which just means if we go back to our particle class, that is that very first override, or initialize, where we're setting this where, and then we're using default values for everything else. So we can override that, and we don't need to use this base implementation. If we don't want to, we can override and just replace it completely. And then we have the update particle, and this also is a hook method. Again, we're passing that particle as a reference, so we're updating the specific particle in the array at that memory location, and we're just applying the linear dynamics that we've talked about before and the angular dynamics we've talked about before in terms of acceleration, velocity, and motion. So we're just updating all those values, and then the time since start value. So this is basic Newtonian physics in terms of the movement, which is going to work for most particle systems, but sometimes you need to do some special things, or maybe you don't want it to act in a Newtonian manner at all, in which case you'd override and replace all this functionality. Then we also have the override methods that are the methods from our Drawable game components, the ones we're overriding there. For example, loading content. And I told you before I'd show you how to initialize those static variables. So we're checking to see, has this actually been initialized? If it's null, we create a brand new content manager. And because we're inheriting from game component, we have a game property, which is the initialized game. So we can just invoke its services and set up the content like that. We could have instead, another possibility is to say game.content and just use the built-in content manager of the game itself. That's perfectly fine. You could do that instead rather than creating a brand new one. But this gives us the flexibility that if we're doing something crazy like dumping all the content that was preloaded, this just ensures that this particle system still works the way we expect. And then we're also creating a sprite batch in the same way. Then we check to make sure that there is a texture file name defined. If there isn't, we throw an invalid operation exception with this nice method describing that, hey, you have to give me a texture file name or I don't know what I'm supposed to be drawing. So that just makes sure that that's there. Then if it's there, we can go ahead and load that texture, and then we can calculate the origin vector values. And that's really all we need to do in our load content, because we only have the one texture for the particle system. That's really all it's using. Our update method, this is going to update all the particles in our system. So first we figure out what the elapsed time is. We precast it to a float, which just makes it easier to work with. We're going to iterate over our array of particles, and for each particle, if it's active, we're going to invoke the update particle method on it, and of course we're passing in that individual particle as a reference, so we're passing in the memory location, the actual particle we want to update. And then if the particle is not active, after we've done the update, we're going to add it to the queue of free particles so that we will update it then. And then we get down to the draw, and in this we're just going to draw all the active particles. So we begin our sprite batch. Notice that we're actually triggering that with a blend state that's defined for this particle system. And then for each particle, if it's not active, we just continue, so we don't do the draw for it. And if it is active, then we'll go ahead and draw it. So we'll invoke spriteBatch.draw. We'll use the textures shared amongst all of them, and then we'll use the position, color, rotation, scale, and other details from the sprite batch itself, or from the particle itself, and then the texture and origin are defined here in this particle system and shared amongst all the particles. And that's basically it for that. Then we have a couple helper methods that are protected that would be invoked by the derived classes to add particles to the particle system. So this one adds them at a specific point in space, and we calculate how many particles to add by basically picking a random number between that min and max number of particles to add. And then we have a for loop, and we're checking to see that we're less than that number of particles, and also that we have free particles left to use. So this will actually stop iterating early if we run out of particles. And once we start iterating, we're going to calculate the index of where we're going to put that particle by grabbing the next free particle index, and then we invoke that initialized particle on that particle and also pass in this vector of where we want to be positioned. We also have a rectangular version of that where we take a rectangular bounding region that we want to spawn particles within. So again, calculate the number of particles the same way. The for loop works the same way, and grabbing the next free particle we're going to work with the same way. The difference is we grab a random position from a random helper within that region. And I haven't talked much about this. This random helper is just kind of a wrapper around a random number generator that gives us some helpful functions. It implements basically random next by passing through from the random, but it also does this next float. So normally you get a double is what you can get from a random number, the random number generator. So this just precasts it to a float, makes it easier that we can just work with floats when we can do them the same way, provide a min and max value and get those. We also have a next direction which creates a random vector in a random direction, a random unit vector. So we can pick a random direction. We can also supply a minimum and maximum angle that random direction needs to be between, and then we can also do a random position within a rectangle. So that just generates a float that's between the left and right side and top and bottom of the rectangle for a new vector. So this is a nice helper class that gets us a lot of that detail done. Okay. So let's go look at our example game. Let's go ahead and implement a particle system. So the first one we're going to do, let's create a particle system to emulate rain. So I'm just going to create a new class. We're going to call this rain particle system. And make it public, and we're going to extend from that particle system class. Okay. So with rain, we're going to spawn our particles in a rectangle because we want maybe to have them spawn all the way across the top of the screen. So we're going to have a rectangle, which comes from Microsoft XNA framework source, and we'll just define that as a property. And I'm also going to add a public Boolean property, is raining, which will allow us to turn the rain on and off. That way we can set up our system and just have it there for the entire game, and when we need the raining effect we can turn it on. And I'll just use the auto property syntax for that, so it will have a getter and a setter, and it will default to true. Then we have to have our constructor. So a public rain particle system, and we have to take a game because the base class needs that. And then we also need, in this case, want our rectangle, which is the source of the rain. And then we have to invoke that base constructor. And the base constructor takes the game that we got as our parameter in this constructor, and then the maximum number of particles. And I'm going to just hard code this to say 5,000 particles, and we can play with that value and figure out if that's a good value or not. But that's kind of That does seem like a lot. Let's do 2,000. And we'll play, if that doesn't work, we'll play with that value. Then we need to define or set that source rectangle so that we can access it later. So we'll apply it to our private rectangle up there. Okay, now we have to implement also, because this is now abstract, that particle system initialize constants. So we're going to override initialize constants, which is not a public method, it's protected. And what we're going to do in here is we need to say what our texture is going to be. So the texture file name, and if we look at our content, I'm going to use this drop, which is just kind of a raindrop shape. It's actually a little fat. We might want to tweak that so it's not quite so fat, but it'll work for right now. So we'll set the drop, and then we also probably want to specify the min number of particles we want to spawn every frame. Let's say 10, and the max number of particles we want to spawn every frame, and we'll put that at 20. And note that we'll come to that. Okay, so that's our initialize constants. We also need to override the initialize particle so that we can change how our particle's getting initialized. And this is where we're setting in those values. So we could invoke the base initialize particle and then make our changes, but all we're doing in that initialize particle is calling initialize on P, and there's no reason to do that work twice. So we'll just say p.initialize, and we want to provide the right override with the right values, the values we care about. So with this particle, no matter what, we need to tell it where it's going to be in the world. So we're going to go ahead and pass along that vector to where that comes in as a parameter up here. And then we need to think about the other things we need to define. I'd like to give this a color, so we need to find an override that actually has the color in it, and that would be this one with the velocity, the acceleration, and the color. For velocity, I think what I'm going to do is have this come down at, say, about 260 pixels per second. So we're going to take a vector2.unitY. So that's a unit vector in the y direction, and we're going to multiply that by 260. And we're going to assume this is terminal velocity, so basically it's already coming down as hard as fast as it possibly can. There's enough air resistance that any acceleration due to gravity is now being countered. So, but we do have to provide a vector for the acceleration. So we're basically going to say there's no acceleration. It's not speeding up anymore. It's going as fast as it can. So that's our acceleration, and then we need our color. And I'm going to go ahead and use a blue, maybe a really light blue, maybe light sky blue. Let's use that. And then we can provide any of the other parameters that we care about for this raindrop. For example, we might want to set a scale, and I'm going to actually use the random helper to pick a float between 0.1 and 0.3. So that'll give us some variation. Oh, I guess 0.4. Some variation in the size of our raindrops. And then we also need to specify how long it needs to live. I'm going to start with a lifetime of 3 seconds. I think that's enough to get all the way down off screen. So we'll try that out. And notice that we just have that one method. That's really all we have to do inside that initialize particle. We could also override update particle, but we want our particles to follow Newtonian mechanics. There's nothing that we need to change there, so we'll just leave it with the default for that. But the one thing we do need to do is we need to be spawning new raindrops every frame. And to do that, we're going to override the public update method that is actually our game particle systems update. So this update right here, which draws all the particles. So we definitely have to invoke this base update in order to get our particles drawn. So we're going to go ahead and leave that in there. But then we're also going to add new particles by invoking add particles. And we're just going to pass in that source rectangle. So these new particles will appear in that source rectangle, and we'll also put this in as part of a Boolean test is raining. So if it's not raining, we'll just stop adding particles, and that means that the particles that are on screen will stay on screen. They'll keep falling down until their lifetime ends, and then they'll disappear. So that is a kind of natural way to stop that rainstorm. Okay, that's really it for this rain particle system. This is actually a fairly straightforward particle system. And we'll jump into our game itself, particle system example game. And to initialize this, all we really need to do is in our initialize, create a rain particle system, and we're going to pass in this, which is the game itself, and a source rectangle. Let's do a new rectangle, and just so we can see this clearly, I'm going to actually start it at 100 pixels, and I'm going to actually start it off screen, so -20, so it's above the top of the screen but a little bit into the screen. And then we'll set the width, let's use 500, and the height, set it to 10. So this rectangle is completely off the top of the screen, above our screen, but then the particles should fall out of it. And then because we did set this up as a game component, we can just add it to components.add and pass in rain. Alright, let's go ahead and run that. And there you can see we have rain, we have it falling down, and if you notice there is that blank line right there, that means that we've actually run out of particles to allocate. So what we want to do in that case is go back to our rain particle system and say, okay, we need more particles than 2,000, so maybe 4,000. And if we get a nice consistent rainfall, that means that we've done pretty well. So just looking at this, you can maybe start to see some opportunities for doing different kinds of things. Like if you change these color to white, and then this could be a star field, and this could be a scrolling shooter where your plane is just flying back and forth and shooting things. And you've got now a nice background that could be completely different. You could even make these twinkle a little bit. Of course, if you're in space, they wouldn't twinkle because there's no atmosphere to cause twinkling. But that's just a technicality. You can make them twinkle if you want to. But there's a lot of ways you could tweak that. You could also add wind to your rain particle system, probably at the particle system level, and then just basically override the update particle and apply a little acceleration to each particle based on the current wind at that moment in time, so at that frame, and that will give you a nice effect where they'll kind of be blown a little bit, and the amount they're blown is going to vary based on how much you're running. So there's a lot of interesting things you can do just by tweaking where we've started with this, or adding another particle system fairly similar. If we wanted to, well, let's go ahead and take a look at our next example, maybe doing explosions, a very common thing we want in a video game. So let's go ahead and add a new class. We're going to call this one Explosion Particle System. Make it public, and we're going to extend again particle system, and inside of that particle system, our explosion, we need to implement our constructor. We're going to have to take a game, and the game is defined in Microsoft XNA framework. So our game, and then max, I'm going to take max explosions. So this is going to be the maximum number of explosions we expect to show in the game. And then we have to invoke that base constructor. We're going to pass in the game. And then I'm going to take max explosions and multiply that by 25. And the reason I'm using 25 is that is the number of explosions I expect to have, or particles per explosion. So 20 explosions going at the same time, 25 particles per each. And then basically if we need more explosions, we would just increase that number of maximum explosions. We have to do our override of the initialize particle. And in this one, oh, sorry, not initialize particle, initialize. Actually, just override. We want initialize constants. There we go. So in this one, we are just going to set the texture file name to be explosion, which is this texture that has kind of an explosion feel to it. And we'll go ahead and say min number of particles equals 20, max number of particles equals 25. Because this is a larger texture and we're going to really take advantage of that additive blending, we don't need a lot of textures for this. And then we'll also set the blend state to be blend state.additive, and that is actually defined in the Microsoft XNA Framework Graphics namespace. Blend state equals blend state additive, and then we'll set the draw order of this component to be that constant additive blend draw order, so that if we are using it as a game component, this ends up being drawn on top of the other components, so it's rendered correctly. Okay, initializing particles. I went ahead and left this because we do need to do that. With an explosion, we want our direction to be random. So random helper dot next direction, and we want our velocity would be, actually let's just do velocity. It's going to be that times a, and we want these to be a little bit of random speed as well, so we'll also use a random scalar value to scale that by, and we'll say anywhere from 40 pixels per second to say 500 pixels per second. So that's going to give us a nice range of velocities in random directions. So they're all starting at a single spot and exploding in every direction. Then we're going to set our lifetime equals random helper dot next float, and these are short-lived, so anywhere from half a second to a second. So not very long in terms of how long these would exist, which is why we can get away with a small number on screen usually, because they won't be there for very long. And then let's also add a random angular velocity. So these are going to spin. And we'll spin them at either somewhere between negative pi over 2 and positive pi over 2 or 4, I guess is what I'm doing. And let's also give them a random rotation. Somewhere between 0 and 2 pi. So they could be completely rotated anywhere from 0 to 360 degrees. And then instead of calling base initialize particle, oh, actually one more. Let's do the acceleration. And we want this to kind of slow down as it hits the edge, because there's air resistance and all that. And to make this kind of look more like what we're expecting, we'll take the velocity and divide it by the lifetime. Oh, so I need the lifetime before I can do that. So basically what we're saying is we want this to decelerate to the point that it's standing still at the end of its life. So that's why we're taking the negative velocity. We divide it by the lifetime. That's how much it should slow down each frame to get us to where we want it to be. Roughly, it actually ends up looking pretty good if we do that. And then we're going to go ahead and set these up. So we can say p dot initialize. We're going to pass in the where vector for the position. We're going to pass in our velocity for our velocity and our acceleration for our acceleration. And then the rest of these we can set manually. So lifetime, rotation, and angular velocity. And if you really want to compact it, you can just take these and drop them directly into the method, but It should be fine to leave them as variables. It makes it a little more legible. You can see a little bit better what we're doing there. Okay, now on this one we do want to also override the update particle. And in our update particle, we're going to go ahead and let it do its default, so the basic Newtonian mechanics, and then we're going to calculate the normalized lifetime. That's time since start divided by the overall lifetime. And what that really means is we're taking the lifetime, we're changing it to a range of 0 to 1. So at the end of its life, it's going to be at 1. At the beginning of its life, it's going to be at 0. And in between, it's going to be a value between 0 and 1 that's a float. So that's very useful when we want to scale things or do some kind of linear interpolation. And we're going to calculate a alpha value based on that. So 4 times the normalized lifetime times 1 minus the normalized lifetime. And that basically means it will fade in and out over its life. And then we'll go ahead and change the color to be white times that alpha. So basically we're going to pulse how much of this has shown up. And then we're going to scale it as well based on the 0.75 f plus 0.25 f times normalized lifetime. So this is basically going to scale it somewhere between 0.75 and 1 based on its lifespan. So that gives us kind of some interesting, reasonably good looking explosion effects, and you can play with those values if you want. And then we also need a way of putting our explosion somewhere. So we're going to create a helper method, void place explosion vector2 aware, and in this case really all we're going to do is expose that add particles that takes a vector. So we'll just pass that directly, and we'll use this lambda syntax, which is shorthand for if we just opened a body and then invoked add particles and returned it, which of course this return type is void, as is this return type, so that just perfectly works. And so wherever we put that explosion, that's where it's going to appear. So let's go ahead and use this one in our game. And in this case, we really need to keep track of our explosions particle system. So I'll create a private variable for that. We'll go ahead and initialize it the same way we did the rain particle system, but we'll use that variable to hold it. New explosion particle system, this, and I'm going to assume we're only going to have maybe 20 explosions on screen at a time, so I'll do it that way. And we'll go ahead and add this also to the components list. And the reason I need a reference is I want to go ahead and down in our update be able to place explosions. And I'm going to place them wherever the mouse actually gets clicked. So I'm going to create a mouse state variable in here. And mouse.getState. And I'm also going to keep the prior mouse position. So we'll have a mouse state. And we're going to calculate a vector based on where the mouse is. That's going to be new vector2 current mouse dot x current mouse dot y. So wherever that mouse is, that's where the mouse position is going to be. And we'll check to see if current mouse dot left button equals button state dot pressed, and the prior mouse state dot left button run state released. So did the mouse just get clicked? And if that's the case, curly brace there. If that's the case, we are going to place an explosion where the mouse is. So explosions dot place explosion and mouse position. Okay, so we save this, run this. Now anytime I click on the screen, I get a nice explosion effect. And if that is too big, then we can tweak some of the values and scale it back and try to get it to really reflect what you're wanting in terms of that size. But yeah, that's basically the idea there. We might maybe pull back on this scale. So that should make a slightly smaller explosion. Still pretty large. Maybe one there, and then we could also tweak the velocity to be maybe not quite so high so they don't go as far. There, so now we have smaller explosions. So you can kind of see how just tweaking a few values can really affect how these things work. And in fact, just to give you an example of just tweaking a few of those values, let's go ahead and just create a copy of this. And oops, that was the PNG, not the class. So our explosion particle system, I'm just going to duplicate that. So this copy we're going to rename to Firework particle system. And we're going to change this explosion to the particle texture, which is just a single dot. And let's take this alpha transition out. And let's go ahead and add some colors. And so this is just going to be an array. And I'll use the array initializer syntax, just throw some colors in. And we'll pick some interesting colors like fuchsia, red, crimson, cadet blue, aqua, hot pink, sure, lime green, and you can just keep adding colors to this. But what we're going to do is we're going to place Firework, and we're going to do a little bit more logic here. So in our add particle, actually let's go ahead and add a private color variable too. So when we update our particle or initialize our particle, we're going to set our color. So we need to velocity acceleration, we're going to add a color. And this is going to be that global color value that we set there. And when we place our firework, we're going to pick a random color. So we're going to say color equals colors, so that colors array, and we're going to pick a random number, so random helper dot next, and we'll just pick the next index of that array. So colors dot length means that we'll pick a number between 0 and that length value. So we'll pick a random color when we place that firework. And if we go back to our game now, where's our game? particle system example game, we can just add a Firework particle system. And go ahead and add it. Down in here, we will do the same thing we did for the explosions, but this time we'll use the right mouse button. And instead of explosions, we'll do fireworks. Place firework. And if we run this now, if we right-click, there you can see we have a little bitty firework cluster, and that's maybe not quite as big as we want it to be. So if we look at our fireworks particle system and maybe set a scale as well. So let's add a scale calculation. Random helper, next float, let's go between 1 and 5, 4. Oh, that's going to be pretty big, 1 point, let's go 2. So maybe up to twice as big as the particles we were using before. Yeah, so I can see it. I'm not sure how well that's going to show up in the video, so let's go ahead and crank that up a couple notches. 4 and 6, so these will be much bigger particles. Yeah, you can start to see them a little bit better. It's easier if I have it not on top of this rain, which is huge. So that kind of gives you an idea just how quickly we can create different effects by tweaking the texture, tweaking a little bit of behavior in some of the settings. Let's do one more particle system. Let's do one that kind of gives us a trail of sparks following our mouse, so kind of like a pixie effect. So we're going to add another class, and this is going to be Pixie Particle System. And the difference is, because now we want to attach it to an object, every frame we're going to have to figure out where that object currently is. And that is what we call in particle system parlance an emitter. So let's go ahead and add an interface to represent an emitter as well. So a new item, we're going to call this iParticle emitter. And rather than a class, we're going to make this a public interface. And really, we just need to know where that's going to be in the world. So public vector2 position, make that a get and a set. Actually, no, we just need to make sure that you can get it. So it can be read-only, that's perfectly fine. And then we might also want to have a velocity vector. Because technically, if anything gets thrown off of a moving object, say you jumped off a train that was moving, you have the same velocity as the train. Relative to you, the train doesn't seem to be moving, but obviously the rest of the world is. And if you jump off that train, your path is going to follow the speed of the train. So you get that initial velocity. So we may also want to be able to get the initial velocities to make our particle system behave the way we expect. Okay. So when we construct a new Pixie particle system, which inherits from particle system, we need to know what that particle emitter is. So we would want to, oh, not in the namespace, in the class. There we go. And then we construct this Pixie particle system public, and we need to take the game, which means we need the game class passed in, and the also we want that particle emitter. And then we need to invoke a base. Which is going to have the game and the number of particles. Let's just do 2000 for right now. And we'd want to store the emitter in our private variable. Oh, I see. Wondering why everything's being underlined funny. Microsoft XNA.framework. There we go. Okay, so that's our constructor, and then we need to have our initialize constants. And for our initialize constants, let's use the I think I have a circle. Let's use that one. It's a little bit bigger than the particle one, which kind of has a gradient built into it. In fact, the Firework might look a lot better if we use this particular texture. And we'll go ahead and set our minimum and maximum number of particles each frame. Set maybe 2 to 5. because we don't need a ton coming off of this thing. And we're going to also use blend state equals blend state additive. And we need XNA framework graphics to get those blend states. Blend state additive. And we'll also do draw order equals additive draw order. Okay, and that pretty much wraps up our initialize constants. When we initialize a new particle, we are going to want to set a velocity to be the same as the emitter's velocity. So we're just going to grab however fast our emitter is moving. We're going to start this particle moving that direction. We're going to affect this particle by gravity. So we're going to set the acceleration to be in a downward direction. And so that would be vector 2 unit y times, let's make it move maybe 400 pixels a second squared. And then we want a scale. Oops, that's need to be declaring these as vars actually. And we'll set that to be a random number. Between 0.1f and 0.5f, so these are going to be pretty small. And we'll set the lifetime to be a little bit random, between 0.1 and 1.0. So basically from 1/10 of a second to a second. And then we can call p.initialize and pass in our position, which is the where, our velocity, and then acceleration. And then we can, let's go ahead and set a color as well, color.goldenrod. And then we can set the scale to be scale and the lifetime to be lifetime. Okay, so that initializes our particle. And then we just need to override the update method of the game object itself. Again, we have to invoke this update to be able to draw everything, all the particles, but we're just going to add particles each frame, and we're going to add them at the emitter.position. So we're using the emitter's position, the emitter's velocity for all of those particles, and then we need to have in our game an emitter. So we could create a class and wrap the mouse and all that. I'm going to do the easy and dirty way and just add particle emitter to the game itself. So our game is going to be our particle emitter, which means it needs to declare a vector2 that's public, that is the position, and a public vector2 for velocity. And then we can come down into our update. And because we want this to follow the mouse, we can actually just say position equals mouse position. So we can just use that mouse position. But before we do that, we need to figure out our velocity. So we can say our velocity is the new mouse position minus the old mouse position. And that should give us the correct velocity, the correct position to draw our sparks, and then we'll just add this in our initialize as a new pixie particle system. And we're going to pass in this for the game and also this for the emitter, particles emitter, and then we'll also add this to the components list. So now if we run this, we should see, following our mouse, a trail of sparks. And we could tweak how that looks and actually get some different effects. And I'm going to go ahead on that Firework particle system. I think that's just going to look better if we switch from particle to circle. Yeah, see, now you can see it a little bit better, but maybe I scaled it up too much if we're using circle, but you can get the idea. You can kind of play with these values, and maybe this trail is a little too big, so maybe we'll switch pixie particle system and use particle. Alright, then we try that again. Yeah, that's kind of a nice look, because now it's got not as harsh of an edge because we've got that gradient in play. And you can kind of see almost a flying fairy approach effect. So there was a whole slew of potential particle systems you can use in your games. Plus, I think you can see how easy it is to come up with your own particle systems, building off of some of these ideas and just building on top of that particle system. Create your own, make some interesting effects that you can put into your own games. And that's all we have for today.